Welcome to the last session of today's workshop, and Professor Rabeet Singh is going to take now together on gifting and this. All of you know that your dinner will be served at the same place, right? Enjoy. We have a one-day break. Tomorrow, our buses will start for excursion at 9 o'clock, right? And I request all of you, those who are not from here, especially those who are staying in hotels and also your guest house, please join to visit some of the places. Okay, if you are feeling very tired, then we can't help it, but okay. We have arranged, I think, something like more than 50 people can, and it should not be a problem. Okay. Oh, I thought they have this.
Okay, all right. So how many of you have managed to make a board? And
Sunday time, don't get time.
more time.
Because we are coming from Chadha, favorite.
Okay, I can understand that. वो actually पूरा दिन होता है ना एक तो Okay, no problem. So, you made it.
You're right. So what do you do? That's what the okay, this is
Like that.
no, just not that. It's nice.
Then you will get a get very close. Yes. Nice. Okay. You already know about it, right? Okay, so 2 of you have done. All right, so whatever problem we were discussing yesterday, that was not the actual problem because in daily life we never find a infinite world. We did it because it was the simplest problem we can think over. And of course, it's a one-dimensional problem. But the actual system, and not the, I think, even the for the actual system, we get only few examples for which we can consider density as a spherically symmetric, right? So density is spherically symmetric, so we can consider potential is a central potential or the spherically symmetric potential. And for such potentials, we can separate angular part and the radial part, right? So we know that whenever we separate angular part, we get equation for capital R, right? Now let's say if I ask you, what is the boundary condition for capital R? So one condition, which is very obvious, whenever we go far away from the system, your probability density should be equal to 0, right? So at infinity, it should be equal to 0, right? What about at r equal to 0? Not for u. Okay, I'm asking because u is written as r times capital R, right? What is the boundary condition for capital R? Because you would need it whenever you want to construct your solution.
Divergence like 1 over r.
Divergence at 1 over r.
At r equals, you have some finite value of u of r.
Potential goes like that. What about solution? And definitely solution will take care of that. Otherwise, we cannot go at r goes to 0. Anybody? Okay. So I'll show you next slide. Possibly you will get to know about it. So these are the two limits. In because whenever you go at r goes to 0 limit, the dominant term will be LL plus upon y square, right? And this equation can be solved analytically. What is the solution? Solution will come r to the power l. And for u, it will come l plus 1 because u is r times. So now you can see if l equal to 0, then definitely that term l plus 1 upon r square is already 0, right? And if it is l equal to 1, then that problem will never come, right? Because l plus 1 is, let's say l equal to 1, then it will be r square, right? So these two will cancel out. Okay, so that problem will not come. So numerically, what we will do that initially we will start solution. We will take our solution in this form r to the power l plus 1. And why are we converting capital R into u? Why do we need it? Because you must have seen it. First, we get equation for capital R, right? Then we convert that equation in terms of u. Why do we do that?
To separate radial part and it helped to separate the radial part and the angular part.
It helps. No. Whenever we separate radial part,
It came as some function of a special function. We could write it as a special function.
that's so why do we do that? Now remember, whenever we get equation from capital R, it has a second derivative also, not only first derivative also, not only second. So whenever we convert it into u, that second first derivative will go, right? So because if you have first derivative, you cannot convert that into the form of Schrodinger equation, right? You want it in the form of Schrodinger equation. And in the Schrodinger equation, you have only second derivative, not the first derivative, right? And actually, if first derivative would be there, what we want, because we want to convert it into the one-dimensional problem. And in one dimension, we don't have first derivative, right? In one dimension, we don't have first derivative. Like you will, have you ever seen a problem something like d2 psi over dx square plus d psi over dx? Never, right? Never, right? So this way, whenever we we basically transform our equation into the U, which is R times capital R, then full problem can be converted into the one-dimensional. Right? Now, and in this equation, one thing you have already solved, because there is the possibility that we can solve this equation analytically. For example, so let me go back. So, for example, if you're a BR, what is BR? BR is the external potential, like, and it's a spherically symmetric potential. Can you give me one example of this potential? Huh? One wire. Right? We all have solved hydrogen problem, right? And this problem can be solved analytically, right? We don't need numerical techniques. We can solve it exactly. Right? And of course, whenever something can be solved in electronic structure, if we can solve something exactly, that could be very useful whenever you are making a program, because that solution will give you basically reference for your code. You can compare wave function, you can compare eigenvalues, right? So this way you will be able to calculate how much energy is coming in your, how much error is coming in your, right? So, and so if it is not the hydrogen atom, let's say if you have a hydrogen-like atom, so then your external potential will be something like minus Z over R. Like helium plus could be one of the examples. Lithium 2 plus could be second example, something like that, right? So then what we need to put is only we need to put at the place of VR, we have to put minus J over. So whatever examples we will be looking, we will be seeing for different jet, we will see energy and the eigenstates. So I think because in the previous tutorial, we already discussed a lot of conceptual things, right? Same things will be applied for this equation also. So, but good thing is that we know how our solution is going near R equal to 0 and R goes to infinity. So first, what I will do, I'll take a hydrogen atom that is minus 1 over R. We already know the solution for hydrogen atom, right? So once we get to know about that, basically we will be using a kind of code, right? Written code. So once we test it, we will extend that code. So for extension means maybe we can check Hartree-Fock equation for simplest system. And what could be the simplest system for Hartree-Fock? It could be 2-electron system, right? So for that, we would need to calculate Hartree energy, right? Oh, sorry, Hartree potential, not Hartree. Hartree potential is simply classical potential for the given classical potential, whatever we study in electrodynamics. For the given density, rho r, it will be like integration rho r prime upon r minus r prime dy. Right? That way we will calculate Hartree. So in case of a Hartree-Fock equation, we have to subtract self-interaction energy because you have 2 electrons. So this potential should be half of the Hartree potential, 0.5 meters. All right. So if we want to calculate Hartree potential, definitely we would need our integration subroutine, right? Because we would need to integrate, we need to calculate that integration, right? And second thing is, sometimes maybe, let's say, if you want to calculate expectation value of kinetic energy, then you would need the subroutine which will calculate second net need, right? So you should have a kind of utilities like you should be able to integrate whenever needed. You should be able to differentiate whenever needed, right? So these all codes are available in one of the package called DFT. So in this code, good thing is this code is written in such a way that you can change whatever grid you want. So I tell you what is the importance of grid, because if you know about the hydrogen atom, where is the maximum part of the wave function? Where is the maximum part of the wave function? Down district wave function. Near R equal to 0, right? वहाँ पे सबसे ज़्यादा होगा. And जैसे जैसे whenever you go away from the nucleus, it keep on decreasing, and at infinity it will become equal to 0, right? So it means what you need is you can construct a grid something like that. That initially you have a very small state size, but you don't want to miss any information, right? Initially you want to be very accurate, right? Because there you have a maximum probability. But when you keep on going away from the nucleus, after some time, this orbital or probability density will become very small. Then you can take a large step, right? So for that, what people do is you must have heard about the logarithmic mass. So in logarithmic mass, automatically this thing is implemented. Like you can take x equal to log r. So initially it will, r equal to e to the power x minus x. So x equal to something like r equal to e to the power minus x, something like it is stated. So in DFT atom, not only logarithmic mass, you can play around the mass. Like there will be some parameter. You change those parameters. You can change initial state size and the final state size. Okay. So we have everything, and because we discussed a lot of things yesterday. Whenever we try to solve by solving the equation. So I'll show you the solver. Okay. And whatever we have discussed, I'll show you where it is implemented. Okay. After that, we will use DFT atom. We will not look into the solver. Okay. So I'll show you how is it done. And this code you can access using your account, right? Slash Rabeet, then programs, there you can find this. All these
Where?
code, whatever I'm discussing.
Where?
You log in there, then
Okay, SSH.
then slash Rabeet,
Okay, do slowly.
then programs.
Okay. Okay, begin.
Should I copy it?
You would be able to copy it. Cannot change it. बता दीजिएगा अगर
Log into your respective accounts. The account details have been shared with you. Log into the 2.200, 172.16.2.200 server using SSH. The instruction sheet has been shared with you already. And For which data is there. A directory by the name of /Rabeet. In fact, all the files in there.
And let me tell you the reference for this solver. This code has been written by I taken from the website which managed by Power Unity, which is the main developer of Quantum Espresso. So I found it suitable to discuss. So, here's them first.
If anybody needs any help, just raise hand and come over there and help you out. Okay.
Did you get the required codes? And one more thing, because it's a program, a lot of things are getting right, and I can definitely understand whenever you look at a new code, it could be stressful. Like I'm looking at this much information is given, even I got stressed. I have seen whole day I found a lot of things, and which I cannot understand, right? So it's totally fine. We will only discuss some main parts and what we have had discussed yesterday, because I just want to figure out those things. And otherwise, don't basically get any headache. Like just feel normal and just try whether we are able to use that solve, because other things are definitely not that much simple. You cannot make it within 1 day or 2 days, uh, right? So you need to spend a lot of time. So don't worry about that. And okay, so should I proceed now? Okay. So initially, I'll tell you. Uh, So whatever radial equation I have shown you, right? So one question will arise that in which range we should look our energy matrix, right? First question will arise like that. So that range we can choose something like that. You will have a potential V. So you can choose the maximum potential and the minimum potential, right? You can choose the maximum value of potential and the minimum value of potential as a range, right? Because whatever energy levels will be, especially the bound levels will come within that range, right? Uh, Only scattering level could be more than the potential value. Otherwise, your bound state will be within that potential range, right? So the first thing this code is doing, this is calculating EF. EF is the maximum value of the potential, right, which is at the point mesh. Mesh is the highest point you are taking whenever you are making a grid. Let's say you are choosing a 500 point, then your mesh is equal to 500.
It's one dimension 500 or total?
One dimension.
In one
It's a
dimension,
radial
500.
equation. Yeah,
Oh, okay.
it's a one. All right, and because your potential goes as minus z over r, so your maximum potential would be at infinity. You can say like that, right? And second, you calculate the minimum value of potential. So in case of minimum value, you have seen in your radial equation there is a part LL plus 1 upon r square also, right? Right? So you have to include that part also whenever you are calculating the minimum value. But at infinity, you can leave 1 over r square, right, in comparison with 1 over r. But nearby the nucleus, you have to include that. So what it is doing, it has calculated EF, it has calculated ELW. Now, whatever energy eigenvalue this code will look, it will look within this range. right? And somebody, I think you were telling me that something like a suiting method we use. We will do the same thing. Like we will initially we will take a minimum, like E min and E max, right? As a E up and E. Okay, file name. This one.
It's under DFT.
Programs DFT3D HE series and then hydrogen radial dot attachment. Okay. 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 Now I'll roughly tell you about it because we cannot discuss within 1.5 hours. So then what we do is we calculate classically allowed region and forbidden region. And you all know about the classical turning point where your I mean above the classical turning point your kinetic energy becomes less than potential charge, right? So you know that point. And beyond that point, what will happen? Your probability density will start decreasing, right? ऐसे समझो. Everybody, can I? If I want, can I speak in Hindi also? हैं? कोई बाहर से तो नहीं है ना अभी? ठीक. तो समझ करो. आपने देखा होगा क्लासिकल पार्टिकल अगर है ना? किसी पोटेंशियल के अंदर तो क्लासिकल पॉइंट से बाहर नहीं जा सकता, है ना? उस पॉइंट से आगे नहीं है. So in quantum mechanics, it is like your probability will start decreasing after that point because we will still have some probability of finding the particle beyond that point, right? Right? Clear? So we want what we do whenever we solve a radial equation, we match our solutions coming from infinity and coming from r equal to 0 at the classical turning point. Because this is the point where you can use that property I told you yesterday, that if your derivative psi prime r is greater than psi prime l, then energy is greater than the quiet point. That condition can be used here. All right. So this code calculates that classical turning point. So and also there will be a place where it will be counting the sign in the wave. The sign function you can see sin fi minus 1 I point and I minus 1. If it is different, it will count something like that. Something will come. You can say maybe okay. So and so here you can see we use whatever we call this suiting method, because initial energy we will take as E up plus E low, lower E max plus E min upon 2. And by counting the number of nodes, we will decide which energy we should take as a E max and we should take E min, right? Let's say if you want to calculate ground state energy, and if we got a one node, it means we will replace E max by the current energy, and we will keep the E min same as the previous value, right? So that way we will proceed, and here you can see the initial wave function. This by is the initial wave function, and let me tell you, it's not exactly the same U we were looking in the radial equation, because what we do is whenever we convert into the logarithmic mesh, we again got to know that your first derivative arises, and to remove that first derivative, we again convert u something like that, u r upon square root of r. That is your pi. So this initial wave function you can see again comes like that. r to the power l plus 1, and then because this is u, and then you divide by square root of r, which is u. So initially it means we know the wave function, okay? So don't worry about that. A lot of terms are there because we choose a series solution and then we calculate a 1 and 2, 3 terms.
These are guessing point.
Initial. Yes.
This is a guess point.
No, it's a point we already know, right? I have shown you that near r goes to 0, we have the solution r to the power l plus. So we know that what is the value of solution, right? So here we start. So we guess 2 points at least at 0 and the first point. And from there we start building our solution. Here we use the numero method. I think you know about that, right? To calculate the next point, and we keep on building our solution up to the this ICL is the classical turning point. So what we do, we calculate it up to the point ICL minus 1. So this is the first integration, which is called outward integration, which is coming from 0. So we will also calculate the next integration, which we will build from infinity. I'll show you here. This is the point. So here you can see we are coming from infinity. So at infinity, what we do, we assume that our wave function by mesh is equal to dx. Dx is a very, very small value. Okay. So from there, and this by mesh minus 1 is calculated using numero method. So whatever formula we have, with some approximation, we can convert into that way. So then we keep on, coming from infinity up to the classical turning point. So ICL plus 1, and we keep on decreasing 1, minus 1, right? That is why we have written in our to-do. And then what we do is, we say that our wave function should be same, right? At the classical turning point, whenever we bring from both sides. So to do that, what we do here, we scale these two solutions. So scaling is simply this factor. I'll show you this fact is already defined somewhere. This one. This is the value of the solution whenever we come from 0 at the classical turning point. That is YCL. This is your fact, right? Now, if we calculate here, here. So this time, actually, whatever YCL will be there, that is now updated, right? This YCL is coming from the infinity. So whenever we are taking from the right hand side. So it means this is the ratio between the y in the left hand side, y in the right hand side. So if we multiply the current solution with this ratio, that means now we have made sure that our both solutions are same at the classical turning. All right, we can do that. There is no problem in doing that. Because yesterday I said we have to match these two solutions, but we can make these equal to each other. Then what we need to look only that our derivative is also same and nothing else. There is no problem, right? थोड़ा थोड़ा आधा होगा तो ठीक है, कोई issue नहीं है. So and then finally we have to normalize it. So that is what it is doing. Finally, and there is some further step which can be used to update energy. I'll tell you what does it do. I'll give some rough estimate. So if your derivative are not same, right, at the matching point, which is the classical turning point, it means there is a derivative discontinuity, right? Derivative discontinuity. And in quantum mechanics, when do we get derivative discontinuity?
boundaries. I mean, for infinite square.
When do we get derivative? Because you all know that wave function is always continuous for all the problems in quantum mechanics, right?
When the potential diverges.
When the potential diverges, right? So if you have a discontinuous derivative, it means you can just revert that problem, because for a delta potential we get derivative discontinuity. Now you just think in a opposite way. You are given the derivative discontinuity, then it means you can consider at that point a small delta potential, right? Delta potential at that. And by taking expectation value of that delta potential, you can update your next energy, right? In the current energy, you just add that as a perturbation energy, just like we do in perturbation, right? So that's what it does, because using that, it can be converge faster than the without this system. Okay, so that is being done in this solver. So I hope I know that you cannot understand everything right now, but you will now. What I assume, at least you got some idea, right? Whatever discussions we had yesterday, and that those discussions are being implemented in this solver. So now next job is, let's use this solver to solve hydrogen atom problem, right? So in case of as I told you, your solver should take some right number, right? Like if you want to calculate ground state, then your solver should be something like that. That I'll give a number like n equal to 1, then it will calculate ground state. If I give n equal to 2, then it will calculate my excited state, something like that, right? So what it is doing, I'll tell you about the every term. N is the principal quantum number. So it means for hydrogen atom, if we give n equal to 1, it will calculate ground state. L is the angular quantum number, right? So if you want to calculate ground state, what will be your L? Huh? 0, right? It's an S orbital, right? And E is your energy. Initially, you will give some energy, and after that, it will update it and give you the final energy. Mass is the number of points you are taking whenever you are making a grid. All right? Tx is the state size in the original mass, not in the logarithmic mass. In X, not in R. Okay? And R is the basically this vector. Whole grid is there, is stored in small, like from 0 to maximum point. It's an array with the size mass. Square root of R is just square root of R, and R2 is R square. P, what is the potential you are giving for which you are solving Schrodinger equation? All right, and zeta is the atomic number. Like for hydrogen atom is 1, for helium, like hydrogen light systems basically. For helium it would be 2, for lithium it would be 3. All right, and Y is your solution. And remember, Y, whenever you want to calculate solution, you have to divide it by square root of R. All right, so let's use this solver to use this solver. So what we will do is, here you can see we are giving zeta equal to 1 because we want to calculate hydrogen light system. R max is 100. So we have chosen our maximum point 100, right? And everything is written here. We are writing in atomic unit, I think. Not in atomic unit. We will get energy in grid work, and we have to give multiply by half to get in atomic unit. So here we are number of points taken. We are calculating something like this. mass equal, because we are using this maximum point and the minimum point, right? And your mass is simply this x equal to log r, log j dar, I suppose, log j dar, because if you have a helium atom, your maximum point should decrease. So now you have a strong potential, atom will contract, density will contract, right? So this is how we are calculating number of mass points. So automatically, what you need to give, minimum point and the maximum point, and divide by the step size, then you will get the number of points in your mass. Okay, so don't worry about. You all know how to make a grid, so you can make your own grid. So it's all right if you don't understand. Okay. Then what it is doing, because we will need a lot of arrays like R array, square root of R, so it is allocating there. And do mesh is just making this mesh because you are giving it mesh, it's a subroutine there. And then it is initializing this initial potential. So in this initial potential, what we are giving atomic number zeta. We are giving R and number of mesh point, and B port will be your output potential. So I'll show this what is this B out. Here you can see this one. Here you can see it is just 2Z upon R. 2Z upon R. Why is it coming? Because and so in radial equation you can see initially there is a factor of -1/2, right? So what we do is we multiply by -2 in the whole equation. So on one side you will have second derivative, in the other side you will have some value. Then potential will get multiplied by 2, right? So that is why we are getting there -2Z upon R, because that's how this code has been written. So whatever energy you will get, that will be 2 times the actual energy. All right. So this is your potential. So let's run it. So what should be the ground state energy of hydrogen atom? Uh-huh. No. That's in electron volt. What about atomic unit? Don't remember. It's 0.5. So let's see whether we are getting it. Just that. Let me see that. I think so. Let's see. So here we need to print our energy. So here I'm calling this subroutine. I have given n equal to 1 and I equal to 0 because we want to calculate ground state. So let's print it here. Okay. Let's see. So energy is here, E. So I will multiply by 0.5 and then this. This is your energy, 0.5. It is accurate up to how much decimal places? For up to the at least 8th places of decimal, right? Okay. You all can run this code. Okay, computer Morgana, only you need G Fortran, right? You don't need any other package. So we are done with that. Okay. If you want to see the wave function, you can look here, but right now we are not looking there. So here you can store it in a file and you can plot it. You will get to know that it has a 0 node, and you can match it with the e to the power minus r. So okay. So till now we at least you all can run this code and find out the energy eigenvalue of hydrogen atom. Can I assume that? Right? Everybody can do that. All right. So if everybody can do that, now I'll make a 34 program. I'll show you 34 program for helium atom. It has 2 electrons. So if the potential, whatever potential will be in the 34 program, your external potential will be -2 over R, right? And plus there will be half of the Hardy potential because you have to subtract self-interest, right? So I saw that code. किसी को आइडिया है हार्डी फॉक एनर्जी कितना आता है हीलियम एटम का? नहीं ले अभी देखा नहीं ठीक. And so two things we will learn here. As I told you, we will use the DFT atom because I have already shown you the sulfur. We have been implement a lot of things. But now, right now, I'm not going to talk about the sulfur. We will directly use that. And we will see about the Hardy-Fock equation, what is the result for this equation. So, okay. And let me tell you, DFT atom is very simple to install. In case if you want to do it at your computer, just what you need to do is, if let's say you have a Git, right? Git is available in your computer. Just Git clone. Let me show you that also. Yeah. If you have your Git is available, right, in your computer, just copy this link and just make a command clone and just paste this link there. You will get whole folder of DFT atom, and then you just use CMake utility. So CMake dot, just CMake dot, and after that make it. That's it. You can do that. So it's very simple to install. So let's come back here. So in DFT atom, I'll show you how do we integrate, how do we. So here in DFT atom, to make your grid, we have some parameters like to R bin, we are choosing something like this, depending on our atomic number. Why are we putting Z there? There is a reason, because whenever your Z is increasing and you have only single electron system, then your probability density basically contract, right? You will have a strong potential whenever your Z is increasing. So accordingly, your mass should change. Your whatever grid you are making, that should change accordingly, right? So that is why we use our Z. R max point, we are choosing something like this. So there will be some parameter. Okay, so don't worry about that. Just play with that. If you want to know further information about it, so there is a paper of the developer of DFT atom. So there you can find all the information of this mess. So then what we do is we have to create an array for R, which is the grid from 0 to infinity, and then what we are doing, we are taking external potential for Hardy-Fock. This external potential is -Z over R. So don't worry about this one because I was using it. I was reading it from a file with some reason. So just your V external is -Z over R. All right. And then here, what we are doing is. Just a minute. Yes. So this is your potential for which we are solving radial equation. And remember, L plus 1 upon R square term is not included here. That is already in this one. Because that would be same for each spherically symmetric potential, right? So that's not going to change, right? So you don't need to worry about that. So only the potential we will construct external potential and 0.5 EXCH. EXCH is the potential which will include that 0.5 Hartree potential. I have given this name because what we do whenever we go beyond Hartree beyond 2 electron system, then there will be Hartree potential plus exchange correlation potential. So I kept that name here also. So I'll show you initially your EXCH is 0, right? We didn't define anywhere. So maybe we can put it equal to 0 if we didn't give a value. So okay, we didn't give a value for this. So we can, let's say, to make sure that we don't get any garbage values, let's say we put it equal to 0. And then okay, so for that, let me write Hartree person, otherwise we will get confused. So for helium atom, your Hartree equation is something like this: del square minus external potential, which is 2 over R, and plus 0.5 pH. So it's like 0.5 Hartree potential. IR epsilon 5. All right. So now you see this rho r prime, actually rho r prime is equal to 2 pi r. Right? Because for helium atom, if we have, let's say, orbital pi r, we have 2 electrons, right? We have to add the probability density of both electrons, right? Then we will get our density, right? We'll get our density. And in this density, whatever solution for which we are solving Schrodinger equation, that solution is included that in that density. It means we have to solve it self-consistently. Right? Self-consistently means initially we will have some solution and we will take that solution to calculate BH. Again, we will update potential. Again, we will solve phi. Again, we will update potential. And we will keep on doing that until your solution stops changing with some tolerance, right? So that's what we will be doing here. So in this solver, because this is a solver from the DFT atom, so same thing would be there, like ion, L, energy. This is the tolerance EPS you give, and I don't know this number 100 why they are giving. R is just a mass. RP is the derivative of mass. U is probably it's a solution. No, right now I don't remember U, but I'll tell you. B is your solution of which is U. जो P है आपका जो U था वो उसकी जगह. तो अगर हमको R कैलकुलेट करना है, we will divide it by R. So that's what we are doing here to calculate density rho R. And we have first we had integrated PR to calculate the normalization constant because we have to normalize our orbit or density, right? So that's what we are doing. To integrate anything in DFT atom, you have to use this function integrate, and then you will provide RP. RP is fixed throughout because it is decided by the grid. RP you don't need to change. So P is U, So you are basically integrating U square. All right. Then we are calculating a normalized density rho RHO, and once we know our density, we are calculating Hartree potential. And see, the good thing in DFT atom is that you have this subroutine to calculate Hartree potential. So you just need to call this function get BH. You just give whatever density you have calculated, give it there, then it will give you the Hartree potential. All right. So Hartree potential I am storing in EHCH, and I have already told you in case of Hartree pop we have to multiply it by 0.5. That's it. So now it will keep on running until your density stops changing. I'll show you there must be some condition here. Here. I'm putting this tolerant 10 to power minus 6. So whenever your error is what whenever your this U minus V external, not it shouldn't be like that because we cannot. V external is totally different. So let me see whether am I? Yeah, it's a good enough because we are storing previous U in the V external, VEXT, right? So what we are doing? So two things we can do. Either we can see if your potential stops changing, you stop there, or we can say if your density stops changing, you stop there. So what I did, I just I'm checking the previous potential and the current potential. I'm just subtracting these, and if the maximum value of this difference is smaller than 10 to the power minus 6, then your code will stop. That's so. Let's run it. So everybody should be able to run this program. So let me run it. Oh, I have to. So for that, what I did is I have provided a map file, and I had given this command there. So you just need to use this map file. So if you don't explicitly give the path for DFT atom, then this make file will work on every computer because by default DFT atom and the libc takes this path. All right. So just make it. So now you can see a lot of things are there. TS is the kinetic energy, and then extra. I actually I'm printing all the eigenvalues for this Hartree program. So I saw here. So, here. So I'm calculating all the expectation values, whatever expectation values, whatever quantities are there in the Hamiltonian. So there is a kinetic energy operator. So I'm taking expectation value of kinetic energy, then expectation value of external potential, expectation value of exchange potential. So everything I'm calculating and then printing it. So that's what we are getting. So, now I stop a bit. Just check it whether you can do it, and let me know if you have any. And why am I emphasizing for this program? Because the reason is once you understand it, you can build your own code. For beryllium atoms, you just need to calculate two steps, add those two steps, calculate the density, calculate the Hartree potential, then the exchange potential. You would be able to basically build your own. And just keep on doing that. For next atom, you would need to calculate next orbit, something. And you will definitely get to know how difficult it is to solve Hartree equation and and also if we know this code, we can use density function here. So only difference would be, I'll show you. Let's say in place of RT equation, we want to use DFT, right? So if we want to use DFT, what we will have? We will have 1 by 2. Basically, we will be solving one sum equation. So we will have del square minus external potential, which is 2 over R. And here we will use exchange correlation potential. So it will have a sum from Ex0. So the functional derivative of Ex0 with respect to rho is the exchange correlation potential. Phi R is equal to S. That's the difference. Right? Ex0, you know, at least for LDA, I think everybody knows, right? For LDA, what is the Ex0? It has some form, right? Integration rho to the power 2 by 3 something, right? 1/3 will come whenever we take functional derivative, right? Bx will be equal to 1/3, right? Rho to the power 1 by 3. So my point is, whenever you know Ex0, you would be able to calculate the functional derivative of Ex0. You can put it there, put that there, and just do the same thing. You update the density and keep on basically running a loop until your potential is stops changing. So I'll show you one of the code, and basically, if you learn that, you will be able to use any function. So next code is basically I made it in such a way that and that code also using the same solver, but it is taking functional from libxc. And libxc is the library. I'll show you how many functionals are available. So okay, so at least this much you can compile, right? You can get the result, right?
Not running, nothing is running. That is the problem. Network issue.
Nobody is able to compile it. Right?
Yes, sir.
At least, so a second thing I'll tell you, you just install it on your computer. And do it.
I have downloaded it.
Huh?
I have downloaded
Require libxc and all, right?
No, Atom wouldn't require, but up till now, it wouldn't require libxc. But next code will require libxc.
If you do make it, it will complain you because there are some files. It cannot find.
There is no make file.
No,
There is no make file inside the directory.
I.
Make file automatically would work. Sita.
So
Because
I copied here, but this one DFT atom I'm not getting a chance to copy. Nothing is working. So this is not there right now because I haven't copied it yet.
Oh.
And I can't copy either. But also we'll require libxc, right, for this.
It will require. But
But
next code only requires because I'm using for the same
you
file.
using, I thought,
Yeah,
okay.
and because I'm using same file, so maybe.
But libxc required here. I thought you have installed libxc.
1 minute, let me see the code. Now, the 2E DFT will require this. But this is the DFT code for 2 electrons.
Okay.
But the current
The
code
height.
wouldn't require.
Okay.
So I have make file in this
Just okay, you download it. Just run cmain dot. Cmain dot. But it's not installed. Install it then.
Yeah, but you usually require.
There's somebody who has compiled.
Which I think you can.
This is slow, right? Network is very. You know what? I'll show you at least the next code. I'm also basically I'm not running it on the server. I'm running it on my laptop. That's why possibly I can do the videos. Okay, this is the code I made for two electron system, and I'm taking functional from libx. So everything will be there, like whatever base we are making, everything is there, and these are the files in which we will use to store density, potential, and eigenvalues. And I show you the same loop is here. You can see the external is there, and then port potential is there. Port is something we will update, and this potential is basically this port is coming from the effective potential. And because I have given this port in the module, so and that module is common, so it will get updated. I'll show you that module. Import port data. This one. So whenever you call effective potential, your port will get updated. And this port at the same place where we were writing 0.5 BH. So I'll show you how we are calculating it. So here I'm using libx to calculate exchange correlation. So what I can tell only if you just take this code, make file is already available, but just make sure whenever you install libx and DFT atom, don't give any explicit path. But I mean whatever default path it is taking, just install it here. That's it. Then make file will work. That's guaranteed. And after that, what I'll tell you how is it working. Finally, you will see I'm calculating this thing pot. So in this pot, you have exchange potential because in DFT, we never use combined exchange correlation potential. There will be functional for exchange, there will be functional for correlation. So we calculate these separately. So that is why you are saying we are calculating Bx and then Bc, which is the correlation potential, and third is the Hartree potential. And that's what is there in that equation. I think Hartree potential is missing. Oh, sorry. So Hartree potential is there. One more term will be there, plus Hartree potential. So I think you all know about that. It's a big on-sum equation. Yeah. So, okay. So just you remember, what you remember is this, that here we are calculating our exchange correlation potential and Hartree potential. Whatever exchange correlation potential is given in that equation. And the functionals we are taking using this ID. Like I have given ID 130 and first ID for exchange potential we have given ID 101 and for correlation potential we have given ID 130. Now tell me if you are aware with any functional we will use that here. So how? So let me show these functional ID in libx. So just a minute. So in libx, if you go in the source file, and there we will have a file xc functional.process. PIXC functionals.h. There we will get ID for all the functionals. Okay, starting from 1, you can see these are the numbers you need to use. Let's say if you want to use Slater exchange, right? You just change 101 by 1. You will get Slater exchange potential. So you have ID for all the functionals. I'll show you how many functionals are available. So okay, let's go at the final point. 734 functionals are available in libc. And second point I'll emphasize is today almost every electronic structure code uses libc library. Reason is because all the functionals are even implementing functionals is very simple in libc. Because so how is it? I'll tell you a little bit about that. What it does basically everything has been made automatic in libc. So there are some maple files. So in case of maple file, it's very simple to give. I'll show you one of the let's say LDA VXC, LDA VXC, something like that. We go there, and let's say if we choose, we'll check one of the exchange potential. No, I forget about the in Linux. So, so in Maple, actually, what you need to define just the functions, functions of density, and because it may look very weird. Even I don't remember that. So only thing is, you will have a very simple functions, and you don't need to take a functional derivative. Maple will do everything. If you change anything, it will take the derivative and automatically that function will get updated. And because all the electronic structure codes takes functional from the libc, then whatever change you will make, that will automatically will go in electronic structure. So it's the best place where we can implement our functions. So maybe I'll show you that page. libc is working on many functionals. So let me show libc. Here you can see the list, everything. Here, do you know any code where libc is not working? Almost everything, quantum espresso, bus, N2K, I think whatever code I know, Octopus, Games, ELK, CP2K, ADF, so everywhere you can find a libc. So that is why I wanted to give you exposure for that. I have made a simple program, and you can change functional, whatever functional you want in that program. And on that program, you can build your own code. Because after that, if you want to make change, you can make change here. So that is why I wanted to give some exposure for that code. And definitely, there are a lot of things in that code. A lot of parameters are there. Even I don't remember what I did because whenever I was in Niger, I made that. And right now, if you will ask questions like I'll tell you what there are something I cannot tell you. So, I'll tell you. Like in libc, what happens? These functionals derivative are calculated in fractions. You have to combine those fractions. So let's say if I am calculating this exchange potential, so you can see I'm calculating first this d1 row, which is the derivative of density, and multiplying it by d2x, which is coming from the libc subroutine, and multiplying by r2. I don't remember why I'm multiplying by this r2. I can't. Only thing I remember that because I was doing something in quantum espresso, and there was difference in quantum espresso and libc. So this factor was there. So right now I don't remember why we multiply by R2, then take the derivative, and then exchange potential is calculated something that I don't remember. But definitely it will work for 2 electron system. If you want to build your own code, you can just increase the number of orbitals and just whatever understanding you have, you can play with it. Okay, so I'm sorry because maybe on server we are not able to do that. Possibly it would be very good if if I do something, you are also able to do that. But these two code libxc and DFT atom, I'll help you to install if you want to do that, and you can just upload these programs and run on your computer. And Makefile, I guarantee they will work on every computer. Just don't change the path. That's just keep the default path for DFT atom and libxc. Okay. So I'll stop here because I have already thrown out a lot of information, and I can understand because I also face the same thing all day. So I don't want to talk more. Just let me know it. Right now, one thing we can do is you can try to install the code. I'll help you to install everybody. In 10 minutes, we can do that. If you want, because huh? Internet is not working. Should we install? It's up to you all because I'll not really I'll not ask you because I can understand it. It has been a whole day. If you are interested, I'll be here. I'll help you to install both packaging. Okay, so this is there on the server. Here's for it. If you connect here, you have to go /e then program.
You all download the file from the server. I will write the command over there.
Yes.
Just I can use that.
Actually, I was that thing.
Or second thing I can do, I have a our my message. I'll upload it here. Full folder, right?
Everybody just log out of the server and type this command what I am typing over here. User whatever account that you have. Substitute this X with the number that you have been assigned, user 1, 2, or 3, whatever.
I don't know whether for it.
For this, we need to.
IT केवल लेन लाएंगे ना उसी सर्वर की काम
And like download it to your laptop and then you compile it using the program.
No, right now you can't edit it. I tried it.
Yes.
No, it's okay. I have anyway this. Yes. But then or maybe I don't know.
We'll do that. I didn't know whether to take the program. I can
For the Windows user, you can download and install software called FileZilla, and using that, you can download it to your desktop and your laptop. For Linux users and Mac users, you can use this one.
and one more thing, for Windows, I don't know what may happen. You should create a Linux-like environment. So otherwise, I don't know how to do.
I will send the slides, but I have the slides of the tutorial that's for tutorial part I have, but for the exam part, you have to ask one of the yes.
Find some different way installing the
Yes.
which will be like
Namana, I guess. So you give your details.
And
The
one more thing, my email ID is simply my name, Rabeet@phs.ac.in. Second email ID is Rabeet Singh. So both are my name, so you can simply email me in case.
you should have all those handles.
yes, for serial, probably no, not sickness for that. But other than that, rest of them will take. You can, yeah, but yeah, other with the. Okay, I can actually send you the .mk file. If you have interview, you can start. I have the. Okay, so then I can send you the .mk. You should work. So you should just change the. You don't need to do anything. Yeah.
Global installation.
Then you can. I'll send the .mk file. You just copy it and you need.
Thank you.
Here also, I just copied the app for this case. Because they are not making children's.
I'm like that.
Whether I go to the course of
I feel but because it just,
you're traveling from IITs to the place.
it's all right. It just massively, you are interested. Huh? And
Who that person?
around 9:30. Huh?
Not just that, make file is referring to local files. That also I probably will change the part. Doing all this just throwing some error.